Julia Matevosyan. I'm a chief engineer at e-cig. I want to welcome you to our 2023 e-cig monthly webinar series and give you a little bit of background on e-cig. For those of you who are not familiar with e-cig, we are a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of energy transition. We do that through workshops, tutorials, webinars, blogs, working groups, and task force activities, and producing technical resource materials. e-cig also serves in a leadership role with the Global Power System Transformation Consortium, the GPST. GPST's mission is to bring together key actors to catalyze rapid clean energy transition at unprecedented scope and speed. e-cig leads Pillar 1 of 5 pillars, which deals with research agenda for the system operators. More information on GPST can be found at www.globalpst.org. Our workshops and monthly webinars are open to everyone, so please feel free to register anytime on the e-cig webpage. If you are new to e-cig and you like to hear more, I strongly encourage you to follow up with us, and I think you will not be disappointed. e-cig membership will give you an opportunity to participate actively in all of our working groups and task forces. You can find us on the web at www.ecig.energy, as well as on LinkedIn, Facebook, Twitter, and YouTube. Okay, just a few logistical matters before we get started. First of all, the phones will be muted for the duration of the webinar to avoid any unnecessary distraction. For the Q&A, we are using Slido platform. So to ask your questions, please go to slido.com and enter code ESIG28 as event code. The instructions are also below at the bottom of your screen right now. You'll see a thumbs up button next to the questions, and so you can cast your vote to help prioritize the questions submitted. We plan to save 15 minutes for Q&A at the end, and then wrap up at the top of the hour. An email with a link will be provided once the video has been posted, and we also plan to provide short responses to all unanswered questions after the webinar. So if you have a question, please don't be afraid to ask and post your question through Slido. So today's topic will be on performance of future IBRs for provision of bulk power system services. With the increase in inverter-based resources, insight is needed on how to plan the system with a large percentage of inverters. What are the kinds of services needed from the grid-forming resources? What impact provision of the services will have on power system? How should we differentiate between various types of inverter-based resources? A few answers to these questions, as well as the viability of using IBRs for system restoration, will be discussed today in the webinar. I would like to welcome our today's presenter, Deepak Ramasubramanian, and I pride myself at being able to pronounce his last name without stumbling. Deepak is a technical leader at Electric Power Research Institute, EPRI, in the Grid Operations and Planning Group. Deepak joined EPRI in 2017, where his work is an area of modeling, control, and stability analysis of bulk power system, with focus on associated impacts of large integration of converter interface generation. Deepak is active and prolific contributor to this industry. Therefore, breaking Charlie's tradition, I actually decided not to go on LinkedIn and check our common connections, because I know we are working with many people, same people over the years. Again, just a short reminder, use Slido at slido.com with event code ESIG28 to ask your questions. And without any further ado, let's go ahead and get started. Deepak, the floor is yours.
Thanks, Julia Matevosyan. So I'll return the service and say I can also pronounce without stumbling. So, hey everyone, let me share my screen. And go to screen slideshow mode. Ryan, can you confirm you can see it?
Yes.
Okay, great. Yeah, thanks, Julia, for the introduction. And hey, everyone, it's a pleasure to be back at e-cig for talking through some of these topics that we've all been discussing across the industry. And some of the work that I'll be talking about today is to give an overview of the performance that we can expect and we should leverage from inverter-based resources for provision of our bulk power system services. And in doing so, we'll then be able to identify how we can improve upon the state of reliability that we have. We can improve upon the kind of performance that we get and improve our stability of the network. The work that I'm going to be presenting in today's webinar is supported by a large number of projects. There's EPRI member-funded research, and there are also grants from the US Department of Energy. And I would be remiss if I don't mention the collaborators that I've had the pleasure of working with. Lakshmi, Vikas, Parag, Stavros, and Wenzong. We work together here at EPRI, and a lot of the topics that I'm going to be covering is a result of the collaborative work that we do in our group. So as we move towards a system with more inverter-based resources, it is helpful to take a look at the kind of needs and how that needs evolve across our network. So in the past, the power system that we've had is synchronous generator dominated. And at that point in time, we essentially expected or wanted the inverter-based resources to really look at unity power factor operation, minimum fault right through, and not really provide any further associated services to the network, because there was a lot of synchronous generators in the system that could provide the needs of the network. We're in a present situation now where there is increased percentage of inverter-based resources, and that has resulted through FERC orders, IEEE standards, and other associated grid codes. There has been now the capability that is required from inverter-based resources to provide services such as automatic voltage control, frequency response, and right-through behavior. Now, note that this is capability, which doesn't necessarily mean that it is always going to be utilized. As long as the capability is there, the delivery of that service itself depends on other conditions, and some of them could be market conditions. But as we move further on in a future system where IBR dominated, and maybe to some extent in few hours of the day, even 100% IBR, we do want to have more services from these resources, from the inverter-based resources. Fast frequency response could be one of them. We want them to help maintain system stability, maybe voltage control. Some of them could be black start, contributing to damping margins, and so on. So the list of services that we would require from these resources would just continue to grow, because we've been so accustomed to that being provided by synchronous generators that which may do it naturally, but for it to be coded up in an inverter-based resource control, we really need to list them out explicitly. And as there is this transition occurring, there might be required, the services might be required to be delivered in different percentages, in different speeds, in different locations of the network, and that will require a lot of studies to be done. So if we have to take all of these services and translate it into some terminology that we'll use in this presentation, let's take a look at these 4 categories. So the way these categories are is I might speak quite a bit about legacy IBR. So what is legacy IBR is essentially the past system, wherein we have the inverter-based resource injecting active power at unity power factor and doesn't really provide any grid support service. So it's just injecting active power, and that those kind of devices would be classified as legacy inverter-based resources. We move on, we have what can be called as a conventional inverter-based resource, which would constitute the majority of inverter-based resources that have probably been connected in the past decade or so. These have the capability to provide voltage and frequency response, but this capability is typically at the plant level, and full delivery of this service may be over a period of multiple seconds. So it's not that the inverter-based resource that's there in our system cannot do frequency response or cannot do voltage response. It's just on a much slower time scale, and it's usually at the plant level. Then we can go towards a different classification of inverter-based resources called enhanced IBR, which can deliver this full frequency and voltage support and response within 1 second of the event occurring. And I will show some examples of that. And if it's part of a network with other enhanced IBRs, then the network itself could survive the loss of last synchronous machine. And finally, we go to a future IBR that is capable of black start and can potentially single-handedly survive extreme events. So it can be designed to tolerate very large extreme events and be stressed a lot and single-handedly survive a lot of such events. So if we take this classification of 4 different categories of inverters, and now we try to apply terminology of grid following and grid forming that we might have heard across the industry, it actually lines up like this. So grid following and grid forming are more of bookends. They're more of bookend terminology, where what is known as grid following in a lot of the material out there in the industry is actually towards the legacy IBR spectrum. And what is known as grid forming is potentially more towards the future IBR spectrum. And a lot of times, this terminology of grid following and grid forming, they refer to a single inverter. But an IBR resource, an inverter-based resource, is usually an entire plant that contains numerous inverters. So you have different hierarchy of control coming into play, and all of that influences the response that we would see. So this continuum of control that exists between grid following and grid forming is important because this terminology, since it refers only to bookends, we have to classify at different sections of this continuum what kind of performance do we want, what kind of services do we want, how does that service differ from the previous bucket of services, so to speak. And now, if we take this outline of the categories that we have and we lay upon it the way these categories are used in power networks around the world, most power networks, and here when I say power networks, I'm talking about large power systems, most of them are still at this position where the majority of the inverters are still legacy inverters. There are few networks that have started using this capability of the conventional IBR. They have started requiring it as a minimum requirement for interconnection, but the deliverability of that capability is not necessarily guaranteed. It could just be that the capability is there and enabled, but there's no guarantee that it's going to be delivered. But across these two sets is probably majority of the power systems around the world. There's very few networks that go into this realm of asking for the enhanced IBR and delivery of this fast frequency response, fast voltage control, and so on. And there's even more few, apart from few small islands, and a lot of active research going on in this future IBR space. So the presentation as it goes along today will focus a lot in these two categories here to essentially talk about how these two categories, the services that we can get from these IBRs, and a lot of them could already be available in the field. It could just be locked because they were not asked for in the interconnection request. So this capability is underutilized because there's hundreds of gigawatts of IBR in the network who may have this capability that is locked up. And there's hundreds of gigawatts in the interconnection queue for whom we are potentially not requiring this capability to be fully delivered, or it's an optional market product. And if we underutilize the capability that we have today from these inverter-based resources, then that can lead to an increased burden tomorrow for a future IBR. So if you have tens of IBRs not providing a service, then the next IBR, the 11th IBR that comes, would have to take upon the entire burden of these tens of IBRs, which means that the next IBR would either have to be much bigger, would have to be much more robust, and so on, in terms of maintaining system reliability. And where that is important to consider is when we consider power system operation, we consider it in a way that, at least the way I like to think about it, is it's a team sport, which means that improving the reliability of the network is better when each player contributes a little in a beneficial manner, rather than the entire burden falling on the most valuable player or the MVP. So if we have each player in the network contributing a little, then it results in a much better operation of the power network. And if we can leverage this capability across the gigawatts of inverters that we have in the fleet and in the interconnection queue, then maybe each of them have to provide only a little bit amount of service, but that can have a lasting contribution on the network. So now if we categorize the services that we require from inverter-based resources, and here we're talking predominantly about interconnected power systems, maybe something like a large interconnection and so on. Some of it applies to small island power networks also, but majority of it is an interconnection network. then we want an inverter to respond in a fast and stable manner to events. We want it to help maintain voltage. We want it to help maintain frequency, and we want it to have robust fault right through. These four categories can be classified better in a team sport manner, wherein each resource is contributing a bit. So say, for example, frequency response, even if you have each inverter contributing, let's say 1 megawatt of frequency response across the entire network, that has a lasting benefit for the entire network because now you have each resource contributing. Black start capability does require MVPs. So we have to be very clear about this distinction between the two, wherein in a black start mode, especially for the first unit that is black starting, we do require specific devices. And if they are inverter-based resources, they might need specific controls in order to provide this black start capability. So if we now talk about this 4 services that are possible from the inverter-based resource fleet, and we contrast it with how we had classified conventional IBR and a future IBR and an enhanced IBR, we now have to delve into some of the controls. So a conventional IBR plant has mainly 2 hierarchy of control. It has a plant controller that is responsible for power control, responsible for providing voltage response, responsible for providing frequency control, and so on at the plant level in a conventional IBR. And then there is a device level control, which is the inverter, which would usually follow the power commands provided by the power plant controller. So the plant level control has principles of droop incorporated into it for voltage and frequency control. And this is typically a slower control over multiple seconds. And the inverter control can maybe either open loop or closed loop, and is usually a very fast control that can have power control enabled on it. Now, if we compare this, so this conventional IBR plant, if we compare it with a synchronous machine has only 1 hierarchy of control. Every controller of the synchronous machine is at the machine level or at the device level. There isn't usually a plant controller. Now here we are talking about our regular transient events, dynamic events that occur for 45 to 60 seconds. We're not talking about some supervisory secondary control for frequency regulation or a tertiary control for market balancing and so on. We're talking about an event happens on the system and we are looking at the behavior that comes about in the 20 seconds after the event has occurred. So if a machine has this kind of control, one of the reasons why it is able to provide a lot of the services that we require is, firstly, yes, natural laws of motion and the physics that it operates under, but secondly, because all of the control is at the device level and not at a higher plant level. So it's by default faster than having something at the plant level, and that difference in hierarchy can play a crucial role in determining stability of the network. So we have gotten used to thinking of a machine with these control, and we've gotten used to thinking of a conventional IBR plant with its plant level control and inverter level control, but we don't often think about the hierarchy of control that exists and the impact that hierarchy plays in the stability of the network and the response of the network. So let's take the first category of service. Let's talk about fast voltage response. So now if you just compare a conventional IBR plant, but now at the inverter level, so we're talking not about the plant level, we talk about the inverter level, it follows power control because it's trying to follow the responses or references that are sent by the plant controller to it, and it has an entire bunch of hierarchy of control inside it. And as you have short circuit strength reducing, as the SCR reduces, you can start seeing an instability come up, which can be reflected both in time domain and in the stability domain. This is not a new result. This has been reported multiple times across literature, and we know that a lot of behavior occurs in this space. But one of the things that we do have to consider here is a lot of times this behavior that we see is not solely responsible because of these inner loop elements. The inner loop elements do play a role, but they are not the main contributing factor for the instability that you would see as the short circuit strength reduces. Because if we consider an example now wherein we move this voltage control, which was at the plant level, we move it down to the inverter level and make inverter level voltage control come about, we can have a response that if you compare versus plant level voltage control versus inverter level voltage control, you can have a drastic difference in response. You can see a drastic improvement in response in the type of reactive power that gets generated, in the control of voltage that happens across the network. And if we now take this behavior and apply it back to the same scenario that we saw, wherein rather than having inverter level reactive control, we switch to inverter level voltage control and keep everything else inside here the same. We don't change anything that is located inside this box. We can now start getting a stable response for short circuit ratios as low as 0.5, both in the time domain and in the frequency domain, stability domain. Now, this is not meant to say that every inverter, if it goes down to this voltage control at the inverter level, will automatically become stable. There is concepts of controller tuning that comes across for every controller that is there in the system. But if this is done carefully, if this is done in a robust manner, then even if we keep everything else the same inside this inner loop, you can still have an improved response, improved reliability of the network by moving from reactive power control to voltage control at the inverter level. So here the hierarchy of control plays a crucial role in determining some level of stability that we want on the network. So the previous examples were for a single machine infinite bus case. We can consider the same example on a distribution network. So if you have a network that is connected to the transmission system through some equivalent, and you have a bunch of feeder elements, and you have a bunch of PV plants, then comparing the response between having this inverter level voltage control on these two PV plants and compare it with some form of future inverter control that is also black start capable, then here's what we come about. So the red curve is the conventional IBR that doesn't have this fast voltage control at the inverter level. The green curve is the IBR, which is the enhanced IBR, which has this fast voltage control at the inverter level. The blue curve is the future IBR that can tolerate even black start or can provide even black start capability. In this particular scenario, we are not looking at a black start capability, but rather we are looking at any system is running for strong systems versus weak systems. An event occurs on the system. Can the inverter control maintain stability? Can it retain stability in the network? And we're not talking about a system going black and then coming back up. Now, this is not to imply that we don't want future IBR technology in the network. We definitely want improvements in control. We definitely want a different set of controls that might come in. But this is meant to show that there's probably a lot of capability in our existing inverters that is not fully utilized. And if we do utilize them, we can improve the way in which we operate the network. We can go one step further in going towards more percentage of inverter-based resources. Now, if you have to understand this from more of a power flow perspective, you can think of it as traditional conventional control of an inverter, which has active power and reactive power control at the inverter level. You can think of it as, from a power flow perspective, as a PQ bus. And if you switch to inverter level voltage control, which would be the enhanced IBR, think of it as a PV bus. And we know from a power flow perspective, we know when we are trying to solve power flow solutions that if we have more PQ buses in the network, the chances that you would get a converged power flow solution reduces. If you have more PV buses in the network, the chances that you have a power flow solution that is converged increases. So the same concept can be applied in a dynamic stability realm, that as you have more of these faster voltage control at the inverter level, you can get an improved reliability benefit. The same thing can be applied, or the same concept can be applied to frequency response also. So we have a similar set of curves here, wherein the blue curve is your conventional IBR that has plant level frequency control. There is a little bit amount of tuning that can be done with the plant level frequency control. And that will give you a little bit improvement in performance, but soon it may become unstable if you try to make it too fast, because there are communication delays involved between the plant controller and the inverter controller. And if you go down to inverter level control or fast frequency control at the inverter level, you start getting a much better response. You start getting a much better benefit. Now, with respect to inverter level frequency control, there have been instances around the world wherein this kind of capability has been required now for a few years. So one example is from National Grid UK, where they have a market-based requirement where an inverter manufacturer could choose to provide services such as dynamic containment and dynamic moderation, where the full response is expected to be delivered within 1 second. And there is a piecewise droop characteristic, which can have a minimum value of as low as 0.21%. So 0.2% of droop response delivered within 1 second. And the expectation is to deliver it in a linear manner and not in a switched manner. There are comparative requirements in Australia that have also come through their market ancillary services product, wherein you can have very fast frequency control ancillary service delivered within 1 second with a minimum droop of 1.7%. And again, the expectation is to deliver it in a linear manner and not a switched manner. IEEE 2800/2022 has also similar requirements for capability related to fast frequency response, although the time mentioned will have to be read carefully, but there is the capability to exceed the requirements that is there in the standard and provide fast frequency response. And a lot of this response is provided at the inverter level and not necessarily at the plant level. So if we leverage this capability that has been asked for, starting to be asked for across the world, then if we consider an example scenario wherein you have a real island network where you have different percentage of PV and battery and DER, and we look at different scenarios wherein, depending upon whether there is frequency control provided or whether there's voltage control provided, if the voltage control is provided at the inverter level or the plant level, or the frequency control is provided at the inverter level or the plant level. And then we try to determine, depending upon how these services are provided at what hierarchy, what is the capacity of a future IBR that is needed to survive the loss of the last synchronous machine. Here we have intentionally not considered fast terminal voltage control because the aim is to see if only frequency control at the inverter level has an impact or not. So if you consider a scenario where there is no fast frequency response that is utilized at all, but rather all the inverters are in some way a legacy inverter or a conventional inverter, wherein there's still some amount of voltage control at the plant level for the PV plants, but the battery is assumed to just inject P and Q. So the battery would be legacy and the PV would be conventional on a slower time scale they're operating. If you do that, then in order to maintain a stable network and meet the UFLS criteria, the under frequency load shed criteria of the system, you need around 23% of a future IBR in the network. And this lines with other studies that have been done, which talk about the minimum percentage of a future net inverter that would be required in the network. But if we actually enable some level of fast frequency response at the inverter level, so maybe we make the battery an enhanced IBR, but we keep the PV still as a conventional IBR, then in order to maintain the network response that we want, we can have the future IBR percentage go down as low as 7% or 11%, depending upon how, what's the criteria with respect to this transient response that we get. So what this is to say is that the percentage of some resource that we might need in our future network is going to be heavily dependent on how much capability of the existing network we utilize. And there is a lot of capability that is potentially going underutilized, which we should be able to unlock so that we can leverage this fast response of the network and go to the next level. Now, there is one aspect here that we do need to carefully evaluate how these fast responses are provided, because fast doesn't always necessarily mean stable. So it has to be appropriately studied, it has to be appropriately designed so that the more number of resources that are able to provide this kind of response, if we go down to fast inverter level voltage or frequency control, the lesser will be the incremental amount that each resource provides, and that by itself reduces the burden on a future resource that we want in the network, which also means that the way in which we are developing requirements for future inverter-based resources can have more specifications added to them in order to ensure that we are utilizing the capability to the best extent possible. There's one aspect now related to stability and damping. We saw about how if we have fast frequency response, fast voltage response, and an enhanced IBR can improve the performance of the network. But all of this has to be delivered in a robust and stable manner. And as we go towards this aspect of stability and damping, there are criteria and various requirements and standards that talk about a damping ratio. They talk about a damping percentage. Now, those are definitely useful. They are definitely beneficial. But with inverter-based resource fleet, we might have to go beyond just a damping ratio. We might have to go down into aspects of frequency domain characteristics, which have been reported also in other aspects of the industry, and we have started seeing some of this come to the forefront. But things like what would be the impedance of the device as seen around the fundamental frequency, or as seen in a short range of frequencies around the fundamental frequency. So we see that a conventional IBR plant would have something like a higher impedance value. A synchronous machine plant has a slightly lower impedance value. A future inverter plant has yet more lower impedance value. And if you actually plot an enhanced IBR response on this, you would see that it lies in between this synchronous machine behavior and the future IBR behavior. We also have to look at different other transfer functions that might provide us visibility into disturbance rejection behavior. It may provide us visibility into whether the controls have sufficient bandwidth or not, and see how they might tolerate different kinds of disturbances. Some of this is still an open research topic, especially to verify if the criteria can be generalized. So we do see some responses that line up. We do see some amount of behavior that may line up, but whether it can be generalized or not across multiple different types of resources and characteristics is something that we still have to do more research on. Finally, we come to the category of black start and system restoration. So there's been a lot of interest to understand if inverter-based resources can provide black start and system restoration capability or not. And there have been multiple studies that have been going on in parallel across the industry. You would have heard of it in different presentations and so on. So I'd like to just talk about one study that we did. It was a collaborative effort with EPRI, SCE, and NREL. And the aim of the study was to try to understand if the capability of an inverter-based resource fleet to provide these services of black start and system restoration, can it be done for a cranking path that was evaluated for a real network? So we had this real network cranking path that we had to evaluate whether the inverter-based resource fleet could really energize the various sections of the network and pick up the generator that was on the other side of the network. It had to successfully energize transformers, transmission lines, pick up load, start up induction motors, and long transmission lines, high voltage long transmission lines, and also looked at the limited availability, because one of the topics that keeps coming up with inverter-based resources and black start is what if the resource is not available? What if we don't have the back-end energy needed to do the black start? And is there going to be an impact on transformer saturation and hysteresis? So a very simplistic high-level view of the cranking path. There are more details that we actually study, but a very simplistic high-level view is you have a bunch of inverter-based resources connected to a 230 kV transmission point. You have to energize the transformers. You need to energize multiple parallel paths of a transmission line, energize some reactors that are there, pick up motor load, which would be the pumping load for these generating stations, and then bring this generating station online. So the way we went about the study to look at the black start capability of these inverter resources is it's very critical that we develop accurate models for this kind of resource, because not just the resource, it's even more important here to develop accurate models of the network, develop accurate models of the transformer, have a good representation of the flux characteristics of the transformer, what kind of saturation we want to enable in the transformer, because if we don't have that representation done in a reasonable manner, then we may miss out on some of the oscillatory behavior that can come up between an inverter-based resource control system and the saturation characteristic of the transformer. Once we do that, look at the energization of the entire restoration path, look at if there is going to be a load pickup that is capable, evaluate if there needs to be a change in the restoration methodology. One of the crucial aspects of these kind of studies that we do is to try to understand that here is an existing restoration plan. What changes are required in that restoration plan when you have an inverter-based resource being the black start resource? Because there might be a need to soft start. There might be a need to have a soft energization. There could be some other perspective with respect to what voltage levels should we meet, what kind of frequency band can we tolerate, and so on. And then would that change if you have a limited capability of the resource that is available? So very high level view of the results looks at how if we do have this variety of factors that are considered, then you can actually make the inverter-based resource successfully energize and black start the entire path. You go all the way from first synchronizing the various inverter plants that are there, then pick up the transformers, pick up transmission lines, pick up reactors along the way to keep the voltage low, and then pick up motor load to be able to start the generator and then make the generator come online. But there is an impact of saturation. So some of the characteristics that we see here with respect to the oscillatory behavior that you see is a result of the nonlinear magnetization characteristics of the network. And that is something that we have to evaluate or ascertain its impact when we are evaluating the restoration of the inverter. Now, a way this can be done, the way a methodology or a method to try to understand some of the impacts of these characteristics of the network and their potential for having instability is looking at some kind of a stability analysis during a black start scenario. So considering that if you have multiple stages of restoration, wherein say you have stage 1 restoration is just looking at this one particular plant that you want to black start and a particular line and pick up some local load. Stage 2 would be to go from here and pick up another inverter-based resource and bring that online. Stage 3 will be together go and pick up some motor load, and stage 4 would be pick up a second inverter-based resource that can come in and help the entire network. Early stages of restoration are typically lightly loaded and also have higher voltage levels. So which means that the inverter-based resources that we are operating in this early stage of restoration should absorb reactive power, and that can have stability challenges associated with it. We've also seen in our studies control interactions occurring between different types of inverter control and different types of load dynamics. So load dynamics is extremely important to consider when you're doing a restoration evaluation, because depending upon the type of load that you're energizing and picking up, it can have an interaction with the inverter control that you're looking at. And some of these interactions are not necessarily visible when you set up an inverter in a single machine infinite bus setup and look at its design of its control gains and its control loops. These characteristics only come about, or they come to light only when you're looking at an entire lightly loaded restoration setup like this, or whatever is the lightly loaded restoration setup. And we've been looking at deriving different kind of stability methods in order to evaluate this at every stage of the restoration process. But a lot of it is still early stage research that hope we have more to share as we do more work on this. So to close out this presentation, the main points that we want to put forth here is that maintaining reliability of a network, we consider it as it should be a team sport. Which means that each device, each player in the network, they contribute a bit, and because of that, the benefits can be tremendous. And in order for them to contribute a bit, there is a lot of this capability that is underutilized or not utilized in the network, which is just lying on the table and not being made use of for the network itself. And if we have to find ways to unlock that capability, that is something that can be really beneficial for the network. So an example of that is increased utilization of fast inverter level voltage control and frequency control that can help improve the reliability of the network. Simultaneously, we do have to go towards adoption of new forms of future IBR control and categorize them from a performance-based perspective. So evaluate what kind of performance we want from them, help make those characteristics and those requirements more specific in nature so that we can really get the maximum benefit out of these various devices for the future network. There is an associated e-cig effort that we are working on. There is a services task force where the objective of the task force is essentially to categorize some of the topics that we presented about here, to evaluate what are the various services that can be delivered either by the enhanced IBR or the future IBR for the future network, be able to quantify the magnitude of service that is required for a specific power network, and then try to understand if the type and magnitude of this service is generalizable across various networks. So if there's anybody in the audience who's interested in participating in this task force, send a note to either Ryan or Julia with an interest, and we can take it from there. With that, Julia, I come to the end of my presentation, and I'm happy to say I made it in time.
Yes, Deepak, perfect timing, thanks. And we have time for quite a few questions, I think. All right, so the first question on slide 4, can you please elaborate how a grid following PV inverter can provide voltage and frequency response?
Slide 4. So a PV plant that is connected today, and actually it might be beneficial if I look at, to talk about this. So the conventional inverter plant that is connected today, it's able to provide voltage and frequency response primarily due to its power plant controller. So by having its power plant controller look at the voltage that is at the POI and have some form of evaluation of the frequency at the point of interconnection, it utilizes some form of droop loops usually, or droop characteristics inside the power plant controller, and it translates that information down to the device level control and changes the P and Q reference of these devices. So which means that essentially the inverter is listening to the power plant controller, and the power plant controller tells it that, hey, we see this voltage event on the system, the voltage is reduced, so increase your Q output so that you can help bring Q voltage back up. So this hierarchy of control is usually at the inverter level, but it can be incorporated into the device level also, wherein instead of this looking at the point of interconnection terminal quantities, it can look at the inverter terminal quantities and provide the same response. So that is how a conventional IBR and an enhanced IBR can provide both voltage and frequency control.
All right, thank you. The next question is, based on what you were talking about, do you think we need to specify inverter level requirements instead of plant level controls for new IBR connections instead of specifying POC requirements?
Yeah, so one of the things there is we do have to be careful, because we also don't want to impose a certain method of hierarchy of control on manufacturers. Like, we have heard of certain plant developers who actually have very fast plant control, and they have been able to reduce the round trip communication time delay across here, which means that they might be able to provide a lot of the services even though it resides at the plant level. So rather than saying where in the inverter control hierarchy it should exist, it might actually be more beneficial to define some of these services based upon how fast should the service be provided. And not just how fast should it be provided, we can also translate this into frequency domain to try to understand what kind of disturbance rejection properties, what is the bandwidth of the control of the entire plant. Because at the end of the day, the transmission planner and the operator, they are interested in what is coming out from the plant. And as long as the characteristics that come out of the plant meet the requirements that we lay out, which could be then structured to try to provide, let's say, this kind of characteristic, it shouldn't really matter whether it is at the plant level or the inverter level. The only reason for bringing out the plant level and inverter level classification in this entire presentation is to try and tie it to how things are being done today in the field.
Sounds good, thanks. Next question is, as we move towards future IBR systems, what are the biggest challenges as you foresee?
Yeah, one of the challenges that we see is that we still may not know how we want these inverters to behave when a fault occurs. We have started learning more about it. We have started learning more about what kind of characteristics we want from these inverters when a fault occurs. But some of this characteristic behavior that we expect for, say, a fault right-through behavior may change with future IBRs because of the way they do their control. So what kind of fault response characteristics, what kind of interaction that might occur with protection elements is still something that is an active area of research, and we need to know more about it. The second a challenge that might occur is how do these inverters operate when they're close to their limits? So inverter-based resources not only have active power and reactive power limits, they may also have current limits. Not may, they do have current limits. So as the inverter operates closer to its current limits, what kind of behavior will manifest and what kind of properties and services can it continue to provide at those current limits is something that we don't fully know yet. And maybe a third challenge that can occur is that with this variety of different control that would be there in an inverter-based resource power system, and not having visibility into that control, because a lot of it is black boxed and a lot of it is proprietary intellectual property material, not having that visibility just increases the challenges in being able to evaluate and understand whether there could be interactions between these control devices and cause some kind of an instability risk.
Thank you. The next question is, how will all IBRs on the distribution system impact what you were sharing? Seems like more IBRs reside there.
So there is definitely, yes, a lot of IBRs on the distribution network. There's gigawatts of inverters on the transmission network, also in the interconnection queue. What we do see is definitely that the distribution network is going from being a passive network to an active network. And what that leads towards, or what that results in, is increased T&D coordination and increased T&D evaluation studies to try to understand not only if the distribution network inverters can benefit the transmission system, but also see if maybe the distribution network inverters could benefit the local distribution network itself with some services that they could provide, and not having to rely on the transmission network. We have done some preliminary studies looking at how, if the distribution network with all of these inverters has to rely on the transmission network, how much of capacity is needed on the transmission network to provide that service to the distribution network, as opposed to if that service was provided in the distribution network itself, the capacity could sometimes be a drastically different number when it's provided within the distribution network itself.
Mm-hmm. Thank you. Next question is, do we need to include inertia in grid forming control both for steady state and transient state operations? Will it affect post-fault recovery?
So it will depend upon what kind of current injection one is looking at. If one requires current injection to be immediate, if one requires current injection to be fast, if one requires the amount of energy exchange between the inverter-based resource fleet and the network to be in different levels of controlled manner, then that will define what kind of performance requirements we want. Now, it can also be possible that some of the performance requirements that we define for close to steady state condition can have an impact on the fault right through behavior, because they might end up being, so to speak, aggressive during the fault, which might then require specialized fault right through control to be enabled. So like one example of this, at least relating it back to, say, a synchronous machine scenario, is the concept of fast valving that was there on synchronous machine turbine control, where if a fault occurred, then we would have fast valve control on the turbines, which would reduce the amount of mechanical power coming in to help control the speed of the resource. So these requirements that we might specify for the close to steady state or nominal operating condition, if they end up being too aggressive or too fast with respect to the response of the network, then they could have a detrimental impact for fault right through, which needs to be carefully considered.
Mm-hmm. The next one is interesting. Why do you think there are many IBRs that are still using plant-based voltage control instead of fast inverter level voltage control? What are the downsides of the faster controls?
Yeah, so I won't comment on why do I think that they're still using. Well, I'll talk about just the downsides that could happen. It's not necessarily a downside. What it brings with it is an improved challenge of coordination. So when you have something at a plant control level, your your decision-making point is at the plant level, and then you can command the individual inverters to react in order to meet your required performance at a particular location. That's relatively easier to take into account. Now, if you move to inverter level control, especially if you look at voltage control, if you look at inverter level control, then you essentially have each inverter on, let's say, the collector network of the system, of the plant, each inverter providing some form of voltage control, which is fast. And along a power network, if you have voltage control being provided at multiple points, if they are not coordinated with each other in a reasonable enough manner, then they could fight with each other. So one of the challenges of taking this control down to the inverter level is being able to have that coordination across all the devices that are all providing this response and still have some control at the plant level. So by transferring some of this control to the inverter level, we don't mean to say that the control that was there at the plant level has to vanish. We still need that plant level control because we still need control at the point of interconnection, which could sometimes be a few kilometers away. So then you need to have a coordination between your plant level control and the inverter level control, which does make it more challenging.
Thank you. You're getting a lot of futuristic questions. Do you see a case in which we stop asking inverters to emulate synchronous machines' performance and reconfigure the grid for IBR characteristics, and synchronous generators are being an exception then?
So my personal opinion here is that inverter-based resource fleet has, an inverter-based resource itself has tremendous capability that can be leveraged. And there is a chance that if we ask them to mimic a synchronous machine, although the advantage of doing that is in some ways a characteristic of performance that an operator might be used to, so they might know how to react if a certain disturbance occurs. But the flexibility that we might leave on the table because we're not still utilizing the full capability of the inverter-based resource might be something that can be impact on the system. The other thing that can occur is that a synchronous machine, the characteristics and response that it provides is a lot of times governed by its natural characteristics, it's governed by its mechanical properties, it's governed by the way it is designed and constructed and built. A lot of those, if you can take those physical characteristics and those mechanical characteristics and write a mathematical equation for it, of course, and then you can put that mathematical equation into a control of an inverter. And when you do that, you are no longer bound by the physical constraints of the device of a machine that maybe restricted the range of a certain parameter in that mathematical equation. So now when you put it in control, you can potentially have an infinite range of that particular parameter's value, which is both a good thing and a bad thing. A good thing of that is that you can probably leverage better response and get better capability, which would automatically deviate it away from a synchronous machine response. The bad thing is that some of the properties that we have from a synchronous machine, which we may not really like with respect to some kind of oscillatory capability, can be reflected if you try to mimic a synchronous machine. So I don't know when and where such a change in trend may occur, but we do recognize that there is a lot of capability that is there in inverter-based resource, and we have to try our best to try to utilize that capability as much as possible, while recognizing that some of it could mean or could imply a slight change in operational practice. But as an industry, we probably have to work together to bring that about.
All right, thank you. So the next question is, or actually priority just changed. Let's get a different one. What is the most recommended approach for modeling IBRs and stability programs for system studies? Detail manufacturer models or generic typical models? And I think that will take the rest of this webinar.
I could have spent 1 hour just talking about that. It depends upon the type of study being done. It depends upon for what purpose the study is being done. It depends upon what system the study is being done, if it's a local level or an interconnection level. So all of that plays a role in determining what model is being used. At the same time, irrespective of whichever model is being used, parameterization plays an extremely important role. So just because one type of model is being used versus another, we cannot afford to go relaxed on the parameter values that we put in that model. So the answer to that question, unfortunately, is just that it depends upon the type of study. And one has to be really careful in trying to make a determination of whether one model type is always suitable or one model type is always not suitable.
Thanks for being concise. The next question is an interesting one. Where does IEEE 2800 fall on the presented transition from grid following to grid forming? That's
a nice question. So I would say that in our experience with IEEE 2800, IEEE 2800 falls anywhere from this scale here, this point here, all the way to maybe this point here, because IEEE 2800 doesn't talk about black start. So IEEE 2800 doesn't ask black start to be like a minimum capability or a technical minimum requirement. So depending upon, and one should realize that IEEE 2800 is actually a whole set of different functionality that can be leveraged and can be utilized. And depending upon how much functionality of the standard is adopted, how much functionality of the standard is utilized, it can fall anywhere from, say, between here to around about here.
Mm-hmm. Thanks, Deepak. The next question is on slide 13. For voltage control at converter level for 69 kV system, are you aware of any studies? Just jump over. Are you aware of any studies which prevents over and under voltage on the unbalanced loads?
Over and under voltage on unbalanced loads?
Yes.
I'm not aware at the top of my head, but I can take that as a note to look into it and respond in the spreadsheet of the questions.
Thanks. That sounds good. I think that will be the last question. A recent example, at the plant controller, there is a hierarchy that the frequency response overrides the set point control there during containment of output. I don't know what the question is, actually. Hierarchy of frequency response that overrides set point control during containment. I'm not sure what is this one asking, actually. So if you had a question, please provide more explanation in the Slido, and Deepak will answer offline.
Yeah.
I think we'll have to wrap up. Thanks so much, Deepak, for this presentation and the audience for your attention and great questions. As I mentioned earlier, an email will go out once the video file has been posted, and we'll answer the questions that we didn't get to, and this will be posted as well. The next e-cig webinar will be on evolution of protection schemes for high share of IBR, so we'll kind of continue the same topic. This webinar will be held on July 20th, and will be featured Steven Sano from Hawaii Electric Company. Further information on all of our webinars and meetings can be found on our website at www.ecig.energy under events, and our newsletters and informational emails are also including this information, and you are all invited to attend. Deepak, thanks once again for this very, very timely and informative webinar, and thank you all for your interest. We look forward to seeing you again in the near future, and in the meantime, everyone, take care, stay safe. Thank you for your participation. See you all soon.
Thank you.
Thanks.